Okay, great. Cool. I'll just start by a brief introduction. My name is Jizhizi. I recently got my PhD degree from the University of Sydney and started working as a research data scientist in Tabcorp in Australia, Sydney. So my topic today would be removing background automatically always user's language. And I'm gonna talk about like around 30 minutes and give you guys a little bit time for the Q&A. So all the contents of today would be including an introduction, some types of literature review, and I'm gonna talk about four papers that we have published in this research field from all aspects of the image mapping, and then talk a little bit about the application, challenges, and opportunities, and then wrap up with a conclusion. Okay, so let's first introduce a little bit about the research topic. This is what we know as removing the background, but the terminology of this one is what we call as image mapping, and specifically that is deep image mapping because we are using deep learning in image mapping. And the deep image mapping is the process of extracting a foreground from an image with a very limited user input, and it is very important in many downstream applications. And as we can see from the figures, once we have an input image I, and the image mapping is formulated to decomposing into the foreground F, background B, and also alpha match alpha with linear assumptions. However, there are a lot of key challenges. However, despite the extensive exploration in image mapping research field, there are some key challenges that always persist, and this is also been the motivation of our research, especially in my PhD study. The first challenge is like the previous method they will always require a lot of human intervention, or we called as extra input, and some of the input would be we called as trimap, and that is a 3-class rough segmentation, including a pure background, a pure foreground, and also some kind of like unknown region. And then another one is we call that scribble based. It is also used to define some pure foreground and some pure background. But as we can say that once we need this kind of auxiliary input, we will need a lot of like extra manual effort to do that, which make that which make that procedure not available, especially in some practical scenarios or some real-time industry scenarios. And another challenge is that previous mapping data sets are very, very limited because some of the research will only provide the foregrounds and alpha match, and you need to generate the final training set or test set by composition, and which will result in a lot of composition artifacts, and I'm going to talk about that later. And some of the researchers will only provide fixed size and low resolution headshots and alpha match, and it is not with very high quality. So based on that, the researchers always use composite images for training and evaluation, and then there will be a very large domain gap, especially when adapting to real-world images, and that will be a very big problem. So to solve this kind of problem, we have proposed a lot of methods, especially in my PhD study, and the contributions can be concluded as follows. So first, we introduce a fully automatic image mapping by decomposing the task into two parallel sub-problems. One is high-level semantic segmentation, another one is low-level details mapping. So by decomposing this task, we are able to conduct the removing background procedure fully automatically without any help of the human input. And we also systematically analyze and solve the privacy issues neglected in previous portion of mapping research. And we incorporate a lot of plugin modules that can help enhance the interaction of the subtasks through shallow and also deep level integration. And the third thing is that we explore the adaptation of automatic mapping methods to non-salient or transparent categories beyond the salient ones like humans and animals. I'm gonna talk about details in the following slides. And the last thing is we collaborate with language modality to achieve a more controllable mapping process. So we enable the removing background procedure by using the user's language. And another good news is that we have published, our studies have been validated through a lot of like extensive experiments, and we provide all the relevant codes and the data size to the public. So by scanning this QR code or visit my GitHub page, you are able to get access to all the codes and the data sets. Okay, so I'm gonna talk a little bit about the literature review about what people have been done. So this is a figure that how people have been working on the research field of image mapping, of the research field of the removing the background from 2016 to 2022. So from the emerging of deep learning to today, and we can see that there are more and more methods and more researchers have been devoted their time and energies on this research field. And I have noted our work by the green mark. And we can say that especially from 2020 to 2023, there are so many people working on this field. So in terms of the mapping input, the user input, we can divide the mapping methods into two types. And one is we call as auxiliary input based. So these methods will require extra auxiliary input information from users, as what we can show from the figure, like some of them using trimap, some of them using background, a cost map, a click, or scribble. And another type is what we call as fully automatic mapping methods. That in this kind of types, they will directly predict the results from the image directly. And in terms of the mapping methods, from the aspects of the auxiliary input-based methods, there are three types. One of them passes through all the inputs for this methods will be image and also the auxiliary input. And the first type, they will pass through a one-stage network and then generate output directly. Another one, they will add outside the module to process specifically on the auxiliary information. And another one, they will use like two branches, and one for auxiliary image, one for auxiliary information, and another for image information, and then they fuse them together to generate the output. And in terms of the automatic mapping method, there are two types of methods. The first one, they pass through a one-stage network using a global guidance. And another one, they use a two-stage network. The first stage is to generate intermediate signal, which is usually maybe the auxiliary input information that we used in the auxiliary input-based methods. And then they use the auxiliary information and also the image to pass through our auxiliary-based network to generate the output. And the problem for this kind of methods is that once they are using two separate stages, the error will be like passed through from the first stage to the second stage, and it cannot be corrected in this kind of flow. And so in this case, we have proposed our own model structure that we're using a sharing encoder to pass through the information of the image. And then we use two different branches. One we name as semantic branch to generate a tree map or generate auxiliary information. And another one is we call as mapping branch to generate a lot of like mapping details. Yeah, so here is a list of all the methods. We have actually published a deep images mapping survey. And anyone who are interested in this topic, feel free to check it out. And here is the data set. Okay, so let's talk about first of our method. In this method, we have a network we name as GFM, which is a glance and focus mapping network. So in this, we have proposed a thing that we call as representation of semantic and the transition area, because we need to decompose the task into two parallel tasks, right? One is semantic segmentation, and another one is details mapping. So how to represent the global information and then the local information is a problem. We have proposed three ways. So the one way is we use a tree map, a 3-class segmentation map, and then the details mapping, the details of the whole image. And another one is the pure foreground and the transition area. And another one is the pure background and then the transition area. So during our training or inference, we can choose one of these three representation, and that is totally enough. Okay, so once we have an image, we pass it through the shared encoder where we consist of like at least 5 convolutional blocks. And here is the heat map of the features that we grab after each convolution block. And once we have E4, the output after the encoder, we pass it through two different decoders. One is we call that glance decoder feature map. Glance decoder here is a feature map in this decoder, and then the output of this decoder will be three class segmentation, which is glance decoder output, and we also pass it through simultaneously to a focus decoder, which is where we get all the details information of that whole image, and here is the output. And for the next step, okay, wait a little bit. For the next step, we're gonna combine these two information together through a module we called as collaborative matching module, and then we have the final alphabet, which includes all the details. So this one is very kind of like similar with semantic segmentation, but it have a very fine details, or very fine, very meticulous details. And another thing is that we have proposed, we have said before, because the previous method have the composition, the composition artifact. So how to deal with this problem? We propose a composition root we name as RSSN, represent resolution, semantic sharpness, and noise. Because previous method, they will just paste the foreground from the image mapping to the background from the Coco image. And we can see the dimension or the resolution of the typical mapping method is like 1000 times 2000. But the typical background images resolution is always like 500 times 300. So if we paste them together, like directly resize them to a very large 1000 times 2000, there will be a lot of like resolution. There will be a lot of like resolution discrepancies. So in this case, we propose a very large data set consists of 20,000 background images. They are all high resolution and they exclude salient objects, and they are very colorful and diverse. So here are more information for more examples of the background data set. We have also published this data set to the public. Okay, and another one is because in photography, we have just realized that they usually use a large aperture and the focal length to capture the sharp and salient foreground. We wanted to simulate this effect by adopting the averaging filter in OpenCV to blur the foreground, to blur the background. So if we look at this image, and we will use some types of the blur to simulate the large aperture to reduce the discrepancies with the real world images. And another one is usually in the data set, they will have some noise discrepancies when they are using the composition. So what we do is we first remove the noise from the foreground and the background, and then we add a global Gaussian noise to the composite images to make it as similar as what we have in the real world images. We have conducted a lot of application studies for all these aspects, and for anyone who are interested, you can check it up to see how these modules will contribute to the performance increase. And we also propose a data set we call as AM2K, consists of 2000 high resolution images of the animals and from 20 categories, including their very fine details, very meticulous details. And here are some of the examples, like these are alpaca and the camel, and these are antelope, cattle, and sheep. Okay, and here are more close-up views of the data set. We annotate this kind of data set by professionals and also by ourselves, and we also publish all the data set to anyone who want to use it. It is under a commercial license. Okay, here is a demo that we have made. We are able to using this kind of removing background on a video automatically, and here is what we have generated from the original video. So this is our all composition video. So this one is original, and the one that you are able to say is the one that composition. Is what we remove the background first, and then we compose it with various backgrounds. Okay, so as we can see, we are able to grab all the details of this animal. We wanted to focus on the topic of animal first, is because they have very fine fur, and it makes the problem very challenging. So we were thinking once we get it done, we could be able to get all the things done. Okay, so this one is some of the demos. Okay, cool. So for the for the second work is we wanted to focus on privacy preserving portrait mapping because we realized that there are lots of privacy concerns and methods in public mapping datasets. Like there are a lot of personally identifiable information of the images in the public dataset. So we propose another dataset we call as P3M10K. It consists of 10,000 images of the portrait images that we collected from website. We blur all the identifiable information, the faces in the images to make it as ethical correct. And we also propose a P3M 500 NP test set validation set. It consists of 500 celebrity images. So we have the face outside, and we are able to test the out of the domain adaptation abilities of this. We name the privacy preserving training setting as PPT setting, and we conduct a lot of information, a lot of experiments on PPT setting to see the effect of privacy preserving training, and we have some conclusions. So based on that, we also propose a method, and in this method, we're including a multitask framework. It is what we have proposed in our previous work. And we have a tripartite feature integration to model the interaction between the encoder, segmentation decoder, and also the mapping decoder. We have a shallow bipartite feature integration to model the interaction between the encoder and the mapping decoder. We have a deep bipartite feature integration to model the integration of the encoder and the segmentation decoder. So basically what we have done is we wanted to reuse the feature that we get from the encoder and to make the full use of that and to try to capture every details as we can. We test, we compare with a lot of sort of mapping methods on our proposed data sets, and we achieve the best results. This one is published in a multimedia conference in 2021, I think. Yeah. So all the code and also the data set, here are some of the results. So our results is on the very right side. So we're able to grab all the details of the human, no matter the face are blurred or not. And also here are some of the demos here. Okay, so we're also able to grab all the details and also be very robust to privacy issues, privacy information. Okay, so here comes our next work. We focus on all types of images because we just realized that the previous methods, some of them require auxiliary input as what I said, and for those that do not require any auxiliary input, they tend to extract all the salient foregrounds. But there are different types of the images in the world, right? So we classify them into three types. One is the images contain a salient opaque foreground, like the images of the animals, of the bear, of a cat. And another one is contain a salient transparent or salient meticulous foreground, like some maybe glasses or maybe some types of transparent objects. And another one is non-salient. For this kind of images, you are not able to define which foreground is salient or which foreground is not salient. So it is super difficult for image mapping methods. And to deal with this problem, first we improve the background. We improve the background because for the previous work we're using like Resonance 34, and due to its lightweight and strong representation ability, but the problem is Resonance 34 is originally designed to solve high-level classification problem, and where both high-level and low-level information are used in mapping problems. So we use the vanilla Resonance 34. But we also use a simple customized modification for this task to try to capture all the details. And we use a unified semantic representation. We present different semantic representation for different types of the images, especially for salient opaque, salient transparent, or non-salient and non-salient. And we get the information. We use a guided mapping process to get the specific process of the mapping using different unified semantic representation. And we also have another dataset proposed. We name it as AIM500. It contains of 500 high-resolution real-world natural images. So all the images are real-world, and it comes from all three types of information and 7 categories like portrait, animal, transparent, plant, furniture, and toy, and fruit. It is actually the largest real-world evaluation data set, and it is making it suitable for benchmarking automatic mating models. And here are some of the experiments. I'm not gonna show details of this. For anyone who are interested, please feel free to check out our papers. Okay, so here are some of the results and also the demos that we prepared here. Okay, so what I wanted to emphasize is this research we name it as referring image mapping. It has been accepted to CVPR 2023 this year. So in this one, what we wanted to do, the motivation of this work is that we realize previous methods, they will either require auxiliary input, or they will extract all the foreground image or foreground objects, no matter they are salient or non-salient or something. But what if the image contains like more than 2 foregrounds, and I just wanted to grab one of these foreground out? Here is what we present RM. We name it as referring image mapping. We wanted to achieve a more controllable task by taking humans' language as guidance. So like so let's have an example. Once we have an original image, it contains a cat and also a human who is taking a photo. And we wanted to only highlight the cat with white and black fur in the image. We are able to do that only using the language. And we want to make the beautiful cat standing on the table, we can able to grab the animal out and paste on green background. And we want to say, please generate the photo of a man with a camera taking photo of the cityscape. We are able to grab that foreground out of and then generate it and paste it on different reasonable background. So the problem for this is also lack of the data set, because we doesn't have any such data set. And what we have done is we making use of the public data sets, public metadata set, and we annotate each entity by their by giving their language descriptions, maybe some colors, maybe some like image resources, or maybe some size, or all the things. And by after this, we compose it the different. We generate a composition engine. We generate some language engine to which we define the basic expression of each entity. We define the absolute position of each entity. We define relative position of each entity. And here are some of the examples that we have in this data set. Like if we have two peoples in the in the image, and we only wanted to grab this woman out. We label the keyword as human, and we label the basic expression like maybe the female person who is dressed in black knit. Okay, so for the method that we use in this topic is we first use clip, and we also use the dual decoder framework, and we have two decoders to process it. And the contribution is, first we have a context embedded prompt that we enable a lot of learnable prompt for the network to learning. And we also have some mapping context, customized mapping context to serve as prefix templates. And the second thing is we use a text-driven semantic pop-up to ensure the text feature from the text encoder can provide a better guidance to dense level visual semantic perceptions. And another one is the multi-level details extractor, where we try to extract all the details of the images and try to preserve them as much as possible. And here are some of the experiments we compare with sorter methods, and we achieve best results in both keyword setting, expression setting, and also the real-world images. Okay, so I want to show some of the visual results here. Like in this case, in the first image, when we have a dandelion and also a kettle, if we only define dandelion, we are able to only grab the details of dandelion out. And in the second image, if we define please grab the foreground of the flame, which is light salmon and non-salient, we are able to do that. And in the third image, which is a real-world image, if we have two persons stand beside each other, and we only wanted to generate the foreground of the woman who is with her back to the camera, we are able to do that. Here are some of the demos that we test on both of our dataset, composite dataset, and also the real-world images. Like if we have two people sit together, and one is woman, one is man, and we wanted to get the lady smells and look at the man, we are able to separate this woman with the man out. So this task can be used very widely on a lot of downstream applications, and it gives you the freedom to use the language as guidance to remove the background of anything that you like. Okay, so for the last work, we published the data set, and we are still polishing. We are still cleaning the code. So once we have done that, we are able to publish also the code to everyone. Okay, so for application of mating, we have a lot of applications that we can use for removing background, like some visual perceptions, like object detection, semantic segmentation, abstract removal, or certain specific mating tasks. So for all these things, the image mating or removing background can be served as a fundamental task. And we also do something like image editing, like composition, image inpainting, out painting, image enhancement, style transfer, and image mating can also be used as a common approach for all these kinds of tasks. And here are some of the examples. Here is what we do on our video mating. We're able to grab the foreground of the videos automatically without any help of the user input. And here is what we use as harmonization. So before harmonization, so what is image harmonization is we wanted to change the color of the face according to the background. So the video you're gonna see on the left is before harmonization, is original video, and then the video on the right side is what we use. Is what we have used our mating works and also the harmonization work. So we are able to change the color of the face accordingly with the color of the background. Okay, so if the background is a little bit dark, the face will be a little bit dark. And then if the background is a little bit bright, the face will be a little bit bright to make it just like he's living in that new video, in that new background. And we also do something like video effects association. This is not our work, it's also some work from others, but this has also shown how we use removing background in downstream applications. So what they have done is they can remove the foreground associated with the effects association and then only leave the background there. So there are also a lot of like challenges and opportunities that especially in image mating, like for the evaluation metrics. Previously, or also in our work, we use SAD or MACE that are capable to evaluating the quality of the predicted alpha mate in terms of the similarities with the ground truth. But they may still exist discrepancies between the evaluation results and the quality perceived by humans. And another thing is that we should focus on designing some lightweight model to make it more practical in real-world scenarios. Okay, so more opportunities like weakly supervised unsupervised learning, multi-modality mating, or also maybe using diffusion model, which is being very, very hot recently in removing background. And conclusion, so in our research, we analyze current challenges in the field of image mating. We're providing solutions for key challenges. Enables the study of fully automatic image mating by task decomposition. We improve the results by designing modules to support interaction and merging between the subtasks. We also focus on the privacy issue of the portrait mating, and we also try to propose new formats of the global representation to adapt the mating results to non-salient and transparent objects. And we also collaborate with a new modality, which is language, to achieve a more controllable mating process. We have also released all the source code and the data sets to the public. Anyone who are interested, feel free to check out our GitHub page. And for anyone who wanted to ask questions or wanted maybe seek some further collaborations, feel free to reach out to me. Okay, so yeah, so this will be my presentation. Do we have any Q&A?
Yeah, so if you want to click on the Q&A box, it does look like we have a handful of questions.
Yeah, I have already seen some of the QA here. So yeah, Ula, I don't know how to pronounce the name. Okay, so what is the difference between semantic and the mating branch? Yeah, that is actually a very good question. We actually go back to this one. So what is the difference between semantic and the mating branch? The semantic branch is able to is designed to generate the semantic segmentation. So it's like a 3-class segmentation, 2-class segmentation, and it is only focused on the global level. And then the mapping branch is used to generate all the details of that full image. So it is what we call as local branch. And one is deal with global level information. One is deal with local level information. So yeah, this is what we have done. What types of filter we use for noise separation? We use actually Gaussian noise. Yeah, this is what we have used. And okay, so yeah, quite impressive. Thank you very much. We have video demos. Optimize the architecture for the encoder. Yeah, so this one is what we have proposed in I think what I'll just say here. Yes, okay, so this is actually for this page. So it is because the previous version 34 they doesn't have the they doesn't preserve the indexes. So what we have done is we customize to make it more suitable for our test. So we modify the convolution and downsampling layers to max pooling layers. In that case, we reserve the indexes to preserve local details. And this is what we have done for the encoders. And another question, after training, did you have any observations about the internal feature space that allow discrimination between foreground and the background? So the internal feature spaces. Yeah, well, actually, we doesn't done a lot of experiments about the foreground and the background, but this is actually a very, very good question. Well, maybe we can conduct some evaluation metrics, or maybe design some evaluation metrics to say what we have predicted for the foreground and then what we have predicted for the background. So we leave it as a further study. How many training data do we use? Normally we're using around 10,000 images, 10,000 images for the training. And sometimes if you want to conduct on a specific category, like maybe maybe only focus on animals, then I would say maybe 2,000 real world images will be enough. And we have all the training data sets public, so you are able to conduct your own experiments on that. Yeah.